Not yet all right. Soon to be all right.
Well, I said without further ado, so somebody has to make me into a liar again.
Yeah.
So.
All right, go ahead. We'll reposition this as I try to figure him, and then try to find my cursor. This is back center. All right. So are we good now? Yep. All right, so this talk, as you probably saw on many of the announcements and on the title slide, is Zeke, a Python platform for teaching mathematical modeling of infectious diseases. Also, to kind of acknowledge the collaborators and the people who pay for this on the outset, Alex Clark, who you probably all know, did a lot of the front-end development. The funding for this, the funding for me comes from the National Institutes of Health, postdoc. The funding for a lot of this and my dissertation came from a Merck Pharmaceuticals investigator-initiated grant. So my background, I'm what's known as a computational epidemiologist. That means we simulate diseases on synthetic populations and find out horrible things that can happen to them. And my background is from an observational epi department, kind of a traditional school of public health. This means lots of stats, not so much general purpose programming. And so Zeke is in many ways kind of retracing my steps from how I ended up as a first-year graduate student doing this to being a computational epidemiologist. And to kind of set the stage for this, this is an informal look at, for the top 2 epidemiology journals in the field, if a paper reported a language, what language did it report?
Wow.
Most of them were written in SAS. Some of them were written in Stata. Some of them were written in R. A few of them were written in SPSS. One hidden Markov model was written in C++. There's some holdouts still using S+. They really want to pay for R. Python is not on this list. In fairness, 2 of my papers are in here and were not written in Python. One was written in SAS and one was written in R. So if you ask people, well, do I have general purpose programming skills? As an epidemiologist, you don't, and you really arguably don't need to until all of a sudden you do. So as a disclaimer, there's not going to be any brilliant new Python today. In fact, the goal of Zeke is not to be particularly brilliant, but to teach kind of basic transferable skills that people can then use, which means there's no pip install Zeke, no from Zeke import star, even though you shouldn't use that generally. It's not a library. It's actually designed to pull from existing libraries. So most of it's written in SciPy, the front end is Django, there's not a whole lot of kind of clever bespoke code. So a brief idea behind why we do mathematical models in EPI. Modeling is actually a fairly established field within public health. Bernoulli did a mathematical model of smallpox immunization in 1760. You'll note, for those of you who are interested in either epidemiology or GIS, this well predates John Snow and the Broad Street Pump. And then the modern incarnation really took off in the 1900s when we started asking kind of active questions about how we fix, especially infectious diseases, with people like Ronald Ross, Reed, and Frost. And this is a really invaluable tool in modern public health. It can illustrate really hard concepts. So herd immunity, which is kind of hard to wrap your head around, it's the idea that at a certain proportion of the population that's either vaccinated or immune, everybody is protected, even if some of them aren't immune. Things like that, or kind of balancing interventions. So do we vaccinate one particular group? Do we try to vaccinate everybody? Things like that. You can illustrate those really well. And then it lets you do quantitative research on difficult, expensive, or otherwise infeasible questions. So how do we want to deploy a vaccine? What do we do about pandemic planning? Since it's in the news right now, this whole Ebola outbreak, you can't really do a study on what happens if Ebola reaches the United States. That hasn't happened. There's no data on it. With modeling, you can at least try to attempt to give some kind of quantitative, repeatable experimentation to some of those questions. But then the question is, how do we teach modeling? And if you're a public health student, the emphasis is on the interpretation and composition of these models. So kind of drawing a flowchart, writing down a series of ordinary differential equations, then magic happens. And out comes a series of curves, and how do you interpret those curves? And from kind of the applied math CS side of things, the emphasis is on the analysis of these models as their own interesting subfield of dynamical systems. What this means is that public health students don't really understand how to implement models. Math students don't really understand what they're implementing. And everybody has this kind of awkward two-part learning curve. You have to learn how to model infectious diseases, and then if you're kind of a math CS person, you have to learn a whole bunch of things about a whole bunch of specific diseases. And if you're a public health student, you have to learn a programming language no one in your field has ever used. So if you compare this to observational epi, observational epi is a field, so people who do cohort studies, randomized clinical trials, things like that, you get this great disease-agnostic general toolkit. You can get through essentially an entire PhD in epidemiology having never actually talked about a specific disease. You can say, disease D is related to exposure E, and there's these confounding variables A, B, and C. You can keep doing that, and they call that biostatistics. Or as you start developing subject matter knowledge, you can start kind of throwing those in and starting to adapt this general toolkit to your system. The problem with mathematical epi is rather than being a statistical model that's talking about your data, a mathematical model is an assertion about how the world works. And so each specific disease has its own specific model, which means for each and every disease, you need to learn at least an adaptation of what you already know. And so this requires very high levels of subject matter expertise required to make a useful model. And what this actually ends up doing is models are frequently borrowed, adapted, or modified incorrectly. I call this modeling by analogy. And so you get a thought process like, well, in graduate school I learned about a malaria model, and dengue is transmitted by mosquitoes too, so I'll use the malaria model for dengue. And then someone asked me about yellow fever, and that's a mosquito disease, so I'll adapt my dengue model to yellow fever. And then if I pretend nurses are kind of like mosquitoes, I can model hospital-acquired infections using my malaria model. And while you chuckle, the dominant model used to model hospital-acquired infections is the Ross-McDonald model, which was originally designed to control malaria. This is a real example. All of these are wrong in subtly different ways. So the solution to this is zombies.
Nice.
So why zombies? So first of all, zombies are familiar. You can become an expert with, a Netflix account or Redbox or Blockbuster, where they still exist. And then you can change model forms without changing the parameters. So you can kind of create a zombie epidemic, and then you can say, well, what if there's a latent period? And then you can kind of add that latent period into the model without changing everything else. Versus when you move from something like measles to malaria, not only have you changed the structure of your model, but all the numbers associated with how malaria transmits are all different. So it's really hard to tell what happened because you changed the structure of the model, and what happened because of all the parameters you put into the model all changed. And then there's lots of room to explore decision making. So the good news is people have been making movies about zombies for a long time. So we have fast versus slow zombies. Can you vaccinate against zombies? Are there a latent period? Are there some people who are immune? Can it be transmitted by birds? All of these things, you can ask these questions without moving out of a single disease system, which you can't really do with any real disease. So Zeke, the actual project I want to talk about, is a web-based epidemic modeling interface. And the idea is it hides the code unless you're interested in the code. So rather than saying, so you're interested in learning about modeling, here's a bunch of Python code. It says, so you're interested about modeling, you can kind of tinker with the modeling. As you become more interested, you can start interacting with the code, or you could not. So it separates disease knowledge, programming skills, and theoretical skills into they're each separate piles that you can tackle independently. And as much as possible, the models, the infrastructure, and the interface are kept separate. This is especially true for the models themselves. The models actually live in the structure of the code in a file called models.py. And those actually can be ripped out, cut and pasted into something like IPython Notebook, and they work as standalone models. They're not heavily integrated into the code so that you have to untangle what's all the front-end stuff from what's the actual science if I just want to know how this model worked. So basically how this works, at least the currently live version, is it lives on an EC2 server, one of the modest little free burstable ones. It has a Django front end from which you can select a couple models and feed it parameters. That goes into the aforementioned models.py, which then goes to a dispatch function. Right now this dispatch function is very, very simple. It just says, yeah, run it. So everything is currently local. One of the things I'd like to develop in the future is sending something to a computation server, or something like Multivac, which used to be called PyCloud. So for some of the more complicated models, so this poor web server isn't also running scientific computing jobs at the same time. This then gets fed into a bunch of matplotlib plotting functions, and then is hosted back in the front end. The reason for choices like matplotlib is, even though that's a less than ideal format for kind of presenting pictures for the web, again, a lot of the plotting code can just be ripped out, cut and paste into IPython Notebook, and you have at least a serviceable publication-ready graph. So the live demo for this, which is always the most perilous part of any talk. Okay, so there's a live implementation of this at zeke-project.org. So this is kind of a basic model. It's called the SIR model. That stands for susceptible, infected, and recovered. Recovered can either mean immune or dead, depending on who you ask and what model. In this particular case, it's dead. And so we have kind of the default values here. We can change these. So you can say, okay, so what if this is worse? And you get kind of a sharper, faster epidemic. If you set this low enough, so if you start learning things about epidemics and you go, man, this beta parameter seems to be really important, you can actually lose the epidemic entirely. That's essentially this disease isn't good enough to trigger an epidemic. Yeah. Please hold. Your call is important to us. You can screw this up entirely. And if it catches an integration error in SciPy, we spit back a value that's like, yeah, don't do that. And then you reset and you're back. And we have a couple different ones. We have one called an SEIR model. The E just stands for exposed, so that's a latent period where you're not yet infectious, but you're turning into a zombie. My personal favorite is one we call Safe Haven. It's a somewhat more complicated model, and essentially what this does is the susceptible people can run to some place that's safe, and while they're safe, they're both less likely to be bitten and infected by zombies, and some percentage of zombie safe survivor interactions ends up in a dead zombie. And if you kind of take the default parameters, you end up getting something that looks eerily like a zombie movie. Everybody kind of runs to a safe place. There's some zombies around, and it's a little scary. So everyone runs to a safe place. Over the course of the movie, it's mostly stable. And then there's some critical threshold where the zombies get through the back entrance of the mall. A bunch of people die, and you're left with some survivors at the end. So I like this model both because you get essentially a Hollywood script out of math, and also one of the things I found for public health students, having not implemented models, is they don't necessarily realize how sensitive some of these models are to changes in parameters. So right now there's this particular parameter called kappa, which is the probability that a sheltered survivor interacting with a zombie will end up with a dead zombie. At 5% you get this. At 10%, the epidemic changes entirely. You get some dead zombies, but you never really get a serious epidemic. If you slide much above 10%, basically nothing happens whatsoever. So you have this model, you have this parameter that kind of takes place at the periphery of the model that ends up kind of driving the entire thing. And that, I think, for people learning how to do this is a really valuable bit of discovery. So that's essentially it for Zeke.
How do I get the models out of it?
There's a GitHub repository that I will link to at the end.
Gotcha.
That's also on the About page. So the figures for this, in case the internet didn't work. So kind of where this is headed, one of the things we'd really like to do is introduce stochastic models. So what I actually do for my job is stochastic modeling of infectious diseases. So that asks for small populations. The impact of randomness comes up a lot more. So if you have a probability of someone being infected at 0.5, for a huge population, 0.5% of the United States being infected is not a big deal. If you're talking about a single nurse, you can't have half a nurse infected. That either needs to be one nurse or 0 nurses, and that has, it turns out, a really big impact on disease dynamics. Curve fitting, so if people want to kind of come with their own data and fit these models and say, okay, so what does my disease look like? And then network or agent-based models. So kind of introducing people to more types of models that, again, with kind of small toy examples, they can kind of get a feel for them and then scale that up to how they want to actually tackle their project. Documentation and testing. Right now, the documentation is made up entirely of this same talk given at SciPy this year. I'd like to fix that. And then testing. The tests are, Alex created a test script, and it has nothing in it.
Well, that's about right.
Yeah, we'll get around to that someday. That is, if any of you who work with scientific code, tests are kind of low on the list of things we want to work with. And the actual kind of scientific goal of this is an adaptation of this as a web-based modeling framework for non-technical users. So these types of models are used very heavily in epidemiology. They're also used very heavily in ecology. Some parts of economics use this. Basically anyone who uses ODEs. And this was actually inspired partially by a dearly beloved member of my committee who, when trying to schedule a meeting, said, "My computer doesn't work with Doodle." So he does, however, have questions about the models I've come up with. And things like, so the hand washing rate in my hospital, I think, is closer to this than the number you've come up with. What's the impact of that? You really can't go to him and say, like, well, so first you're going to install Anaconda, and then I need you to go to this GitHub repository, pull that down, change some things, run the model. So it's much easier to point them to this and say, I don't know, put in your number. And now it will come a graph. And if that graph looks scary to you, that's something you should worry about. If it's not, don't. So that's the actual goal of this, was to kind of develop an interface that you can hide the models as much as people want them hidden, but that there's this kind of rabbit hole of development where you can start heading down as you're interested. So if you are interested, we are looking for contributors. One of the goals behind this was also meant to be an approachable project for new open source contribution. It's written in Django and SciPy. There's no scary Fortran code. I'd like to think the code is not entirely spaghetti. It's meant to have a lot of kind of little targets. So if you just want to, contribute to an open source project, fix a particular thing. And the nice part about keeping things separate is you only work on the bits you actively want to work on. If you're a front-end developer, please, please, please work on the front end, because I'm not one. And similarly, if you're really interested in kind of the scientific computing stack, there's lots of different scientific computing applications here, or kind of the link with the back end. There's lots and lots of possibilities there. That's the GitHub repository, github.com/epimodels/Zeke. And there's currently live deployment at zeke-project.org. Thank you very much. These are ways to get in touch with me. There's a Zeke-specific email address, zekemodels@gmail.com. That goes to me, which is eric.lofgren@gmail.com. My Twitter handle is Germs and Numbers. And there's both the GitHub for the Zeke project, and also this was inspired actually by a series of essentially introductory workshops I gave on modeling infectious diseases using zombies. So for that, there's both Python and R code. And presentations that kind of walk through what these models are, what they do, what the equations mean, and that's it. So thank you very much.
Questions?
Comments? Scathing criticism?
I'm still slightly flummoxed by kind of how you managed to expose, because you didn't show kind of the exposition of the code. Could you show us a bit of that?
Sure. Let me
actually see the code.
Where's my poor cursor? Yes, here we go. We'll bring Firefox back up.
Can you repeat the question?
Yeah, so the question is essentially, so how is the code exposed? All right, so live typing. So basically, this should look familiar to anyone who's done Django projects. And then in Zeke, the real core of it, so there's all kinds of the just generic Django front-end stuff. You can work with, we've got a couple different pages that are all in templates. And then the core computational part of it is in this models.py statement, which does just have essentially each of these to about here is a single freestanding model. So you could, like I said, cut and paste that into your editor of choice, run the function. and you should get out a time series of what will end up making those curves. And then similarly, somewhere there are plotting functions that do the same thing, and then all the front end stuff. Does that make sense and adequately answer your question?
It does, thank you.
Anybody else?
So are you bringing this to professors at universities? Where do you bring this?
So the inspiration for it was the last time I tried. So I've taught this workshop twice, and the first time was a half-day workshop, and they said what we'd really like is a full-day workshop where the second half was hands-on tinkering with these models. So I said that's great. I'll pick the closest language to what you probably all know that has built-in, decent ODE solvers. We'll do this in R. That was a fiasco. It's really hard to get people to essentially learn how to code on the fly. So part of the point of this was I'm going to write this for myself, and then take it to whoever wants it. So, but part of it is indeed that trying to get professors to adopt this as, so if you're teaching an introductory modeling course, you can essentially either work off our server or run your own server and be able to play around with a lot of these models. You could have a student project that's, design a model and contribute a pull request, things like that. You could rip this out entirely and have, we're going to do all theoretical ecology models, but the class project is to write a functional set of theoretical ecology models. And then the second half of it, which is actually kind of the inspiration and where Merck was funding it, was the ability to hide the computational machinery of modeling from subject matter experts and have them still be able to interact with models. So be able to go to a meeting, have someone say, yeah, but I think this number is wrong, and kind of be able to interact with that rather than having to, go back to my lab, fire up my computer, run a bunch of code, come back to them, say, no, it turns out that doesn't matter. Just be able to kind of do that on the fly and have them be able to interact with their own tools. One of the actual goals of my lab is we've developed, this is actually a fairly simplistic one, we've developed kind of the same philosophy for some very large-scale agent-based models, a lot of graph theoretic algorithms and things like that. So you can start interacting with these kind of high-performance computing tools without actually needing to know a lot of high-performance computing, having access to your own cluster, things like that. So there's a lot of different directions it can go, but part of the inspiration of it was just, I want it, and then if anybody else wants it, that's awesome. Anybody else? All right.
Just, you talked about analogies and models.
Mm-hmm.
When building models from various diseases, are there fundamental building blocks in terms of putting those things together so that you can have something? I don't know if that made sense.
Yeah.
Like, for example.
So the basic structure of almost every mathematical model in epidemiology is that SIR model. The progression of people from susceptible to infectious with some endpoint. Basically, all models are elaborations of that. How many different kinds of susceptible do you have? Whether recovered is removed or dead, or if you have both, or you have some states where then you can wander back from recovered to susceptible, things like that. So essentially there's that kind of single chain building block, and then you end up gluing complexities onto that. All right, well, thank you all very much. Will anything explode if I unplug this?
Nope.
Sweet. Yay.
So next up is Charles with Flask and Angular, and he's going to need a minute to set up and microphone transfer. So talk amongst yourselves.
Where's the bathroom announcements?
Oh yeah, actually, wait. If you guys want to do announcements, if anybody's got announcements, let's do them right now.
The bathroom was through this door, straight through the hallway. Get to the exit door, go through them, and then go right into the on the right somewhere there.
Might be locked.
The guy showed us where. Oh yeah, it's not going to be open in there. Yeah, they're not
What kind of announcement?
Any announcements at all? Somebody hiring somebody? Oh, we got one.
Hello everyone, I'm Rami. You're going to see me up there in a couple of minutes. I work at Social Tables, which is a startup here in DC. We're based in Chinatown. We don't use a lot of Python. I'm trying to change that slowly but surely. If you want to help me out and want to write some really interesting code, solve some challenging problems, come look me up.
Okay.